Welcome everyone, and thank you very much to the conference organisers for the opportunity to present this research paper. My name is Stephen Pickard and I'll be presenting on behalf of the team, which includes Associate Professor Dr. Ami Edels, Dr. Eric B, and Dr. Leslie Blaha. In the paper, we cover the initial stages of research being undertaken as part of a PhD program through the University of Newcastle, Australia. Based within the aviation context, this research is attempting to detect a loss of situational awareness using detection response task. The research is in two phases, an initial survey phase and then an experimentation phase. The survey has been distributed attempting to gain an understanding of what current aviation personnel understand of the construct of situational awareness, how it is currently taught and assessed, and what are the observed indicators of a loss of situational awareness. The survey results will be used to validate some previously identified elements of situational awareness and the link to cognitive capacity and workload, and the cognitive and physical indicators of a loss of situational awareness. The survey results have provided input into the design of the experimentation phase of the research project, which should commence in the near future. In the experimentation phase, a DRT-style experiment using a platform called Modifiable Multitasking Environment, or ModMe, will simulate pilot workloads and behaviours, and through gradual increases in workload, use the DRT responses as a cognitive performance indicator of a loss of situational awareness. Firstly, let's provide a quick definition of situational awareness. Though the term situational awareness is commonly used in aviation, transportation, and increasingly in other industries, there is still debate around the most appropriate formal and operational definitions. The diagram shows the most widely accepted model by Micah Ensley. To summarise the model, information is perceived through the senses in the form of stimuli. These stimuli are then attributed meaning and importance during the comprehension stage by comparing the incoming information against different or additional stimuli, other information held in working memory, or models held in long-term memory. From this comprehension of the information, the situation is then projected into the future to determine possible outcomes. Based on this projection, decision or response is selected and then executed. Feedback on the outcome of the selected response is gathered via the senses and will indicate either support for the decision in that it was correct or determine that an incorrect course of action was selected and the process recommenced. The diagram also shows some of the factors that can impact on the process from both internal and external perspectives. Situational Awareness Survey was implemented online using Lime Survey, which was hosted on the university servers and allowed email distribution of the survey link and management of the results. The survey consisted of 76 items in 6 sections. Section 1 identified demographic data around an individual's current role and experience. Section 2, questions pertain to the participants' background of situational awareness training and assessment through their initial pilot training. Section 3 asked about the participants' current understanding of situational awareness based on descriptions identified in a literature review. Section 4 contains similar questions to Section 2, but relating to training and assessment in the respondent's current environment. Section 5 asked questions related to the respondent's observations of when someone is losing situational awareness. Question 6 was a free-form question to allow the respondents to include any additional pertinent information. A 4-point Likert scale was used for most questions, with response options strongly disagree, agree, and strongly agree. A neutral or middle option was not provided, and respondents had to answer in either a negative or positive way. At points in the survey, negative questions were used to discourage response bias. These negative item responses were reversed during analysis. The target audience for the survey were those currently employed as commercial pilots, recreational pilots, flying instructors, or undergoing pilot training. Demographic data also determined the participants' aircraft types flown. To simplify the approach to potential respondents, organisations with access to pilots were approached to have them distribute the survey to employees or members. The organisations approached included regular public transport operators, Australian Defence Organisation, civil flying clubs and associations, defence industry organisations, emergency services, and other commercial aircraft operators in the general aviation space. These organisations potentially provided access to 12 to 15,000 respondents. The response to the survey was not good. Over the 12 months the survey was open, 15 organisations distributed the survey and only 26 responses were received, and of those, only 24 were complete. Demographics show that all respondents had civil flying backgrounds, no military, and respondents were predominantly pilot or pilot instructors, with only 2 also registering as student pilots. All flew fixed wing aircraft, with 2 also having flown rotary wing, and there were no UAS pilot responses. Experience levels range from 3 to greater than 21 years and from 50 to over 5,000 flying hours. Survey results validated the use of negative questions to identify participants interpreting the questions correctly. Participants generally answered as expected for positive and negative questions. Analysis of the survey data. We use correspondence analysis to explore the survey results and visualize the associations between the outcomes. Pearson's chi-square statistic is typically used to assess statistical significance of the relationship between 2 or more categorical variables. When such an association is statistically significant, this measure is used in correspondence analysis to examine its structure in a low, 2 or 3-dimensional graphical format using a correspondence plot as shown on the slide. To perform the correspondence analysis, the Likert scales were converted into numerical values and a table of response frequencies was constructed for each question. Correspondence plots were then constructed using R code on a table of counts for each section of data. Correspondence plot shown provides an excellent visual summary of the association. This is evidenced by the sum of the X and Y dimensions in the plots being greater than 80%, which is a benchmark of validity for correspondence analysis. In section 3 of the survey, the questions related to the participants' understanding of situational awareness and were developed around the contemporary description from the literature. Correspondence plot was developed for the questions in this section, questions 32 to 49, as shown on the slide. In summary, each point on the plot corresponds to a survey question, and the proximity of the point to the 4 response options shows their association. As can be seen in the correspondence plot, there is a strong association across the responses towards the agree and strongly agree options. For example, question 49, situational awareness is making decisions on available information. Responses were agree 16, strongly agree 8, and disagree 1. Hence the location of the point in relation to agree on the plot. The responses to question 41 were more closely aligned with strongly disagree. Overall, the correspondence plot shows that the respondents generally agree or strongly agree with a contemporary construct of situational awareness as identified in the literature. The questions in section 5 refer to the physical and cognitive indicators of loss of situational awareness. You can see the correspondence plot for this section. Again, there was a strong association between the responses and the indicators of loss of situational awareness in the literature. The respondents indicated agree or strongly agree to question 63. It was easy to detect a loss of situational awareness. They also agreed with the cognitive indicators questions that a loss of situational awareness was indicated by not detecting threats, question 65, a loss of scanning techniques, question 66, poor decision-making, question 69, and not following procedures, question 71. This cognitive element of situational awareness is most interesting and steers towards a concept that experiments that measure cognitive performance and workload can also be used to measure situational awareness or a loss of situational awareness, which was identified through the literature review and now supported by the survey results. From the literature review and analysis of the survey results, the nexus between cognitive capacity, workload, and the indicators of a loss of situational awareness should be explored through experimentation. Such an experiment has 2 main requirements. Firstly, to mimic pilot behaviours as much as possible, and secondly, allow systematic manipulation of the speed and complexity to control workload of the task. The detection and response task is a well-established methodology for observing changes in cognitive workload and capacity and has been used extensively in the automotive industry. There's been limited use of the DRT methods to measure or detect a loss of situational awareness as experienced by an aircraft pilot. The planned DRT experiment aims to replicate pilot behaviours in operating an aircraft as much as possible in a simple interface. The types of behaviours replicated are the use of fine and gross motor skills, i.e. use of a joystick, use of visual scanning techniques to switch between stimuli, mimic some of the stimuli types commonly seen inside and outside the cockpit, and get the participant to use cognition to detect error or threats conditions and project future potential outcomes. It is anticipated that a drop in performance of the DRT will be observable as a rapid increase in response times and error rates and serve as an indicator of a loss of situational awareness. We have identified a suitable platform to run the DRT experiments, which is called ModMe. This slide shows an example of a ModMe interface with 4 individual tasks: a crosshair tracking task, top left, a multi-object tracking, top right, monitoring task, bottom left, and resource management task, bottom right. Each task can be individually configured to manipulate the workload. The software tracks alert states when a user input is required, response times, and errors, which can be extracted for analysis. For the initial experimentation phase, a lower complexity ModMe configuration will be used as shown on the slide. The crosshair tracking task on the right is the primary task, and participants use a joystick to maneuver the crosshairs to keep it centered in the display. The secondary task on the left has 2 elements, a button and a slider, and participants press the relevant function key when they observe an alert state. This less complex configuration with relatively slow-moving stimuli will be relatively easy to complete and provide a baseline in which participants can complete the task with minimal errors and fast response times. Over subsequent trials, the speed and complexity of the stimuli will increase in a staircase manner to track how response times and error rates change with increased workload as a potential indicator of an overload and a loss of situational awareness. This should validate the level 1 of situational awareness. Later experiments would use a similar methodology, but with a more complex set of tasks to measure a loss of situational awareness at the 2nd and 3rd levels, similar to the one shown on the previous slide. This will require participants to scan frequent events occurring in multiple screen locations and monitoring to identify threats and potential future states. To summarize, the Situational Awareness Survey results validated the information from the literature review and help inform the design of the experimentation phase through the nexus between cognitive workload and situational awareness. The ModMe software tool provides an excellent platform for implementing the proposed DRT experimentation. Through the experimentation, we will increase the cognitive load on participants to verify the participants' loss of situational awareness through increased response times and error rates. Before I finish, if there are any pilots in the audience who would like to participate and complete the Situational Awareness Survey, please feel free to email me at stephen.pickard@uon.edu.au and I'll happily send you the link to the survey. Thanks again.